You like our children small. They said, right.
How'd you get that back now?
It's just something that Zoom does. All right, ladies and gentlemen, as you are quite aware, this is the last week before Thanksgiving break. No, that was last week. Sorry. But I will say that this week we do have a little bit of math, but I'm going to show you a shortcut here in just a bit. All right, so I've got week 13 notes. You'll notice there's a worksheet. I'll tell you more about that one in just a minute. We're going to go to week 13 materials. I also provided 2 of these things. I'll tell you more about those. This is last year where we got shut down. So I've got a little bit of stuff prepared. I had to do a couple of things for a specific heat, which we're going to talk about in just a moment. Yes, so do I. It's fancy. Oh, my mask too. Oh, Lord. Okay, then. I didn't realize that. I guess it's the same. I guess if I just wear blue up here, I could just be a floating head. All right. So, also, I am recording these mostly because y'all are a little bit more inquisitive than my other class, a little bit more talkative. It's easier to engage questions out of you. So this is temperature and heat. So what is temperature? Okay. You say that temperature is a type of energy, right? So if we are, like, let's say that we're driving down the road. Is the speedometer measuring the amount of energy that is in those tires?
No.
No, it's just measuring how fast something is moving. Now, you're not entirely wrong. Temperature is a measurement of heat. What's up? I'll deal with it later. That's gonna be my biology class. I'm gonna get on them. They won't be able to work in groups anymore. Yep, that's LJ. That's LJ. All right, so temperature is a measurement of heat. Heat is a type of energy. So you were on the right page, Najee. We use temperature as a measurement of how much energy is there. You can think of it as a speedometer for molecules. Temperature is simply the measurement of how much energy something has. The hotter it is, the more energy it has. The colder it is, the less energy it has. Measure of average kinetic energy of particles in an object. So the hotter it is, the more kinetic energy is happening. So the temperature of hot tea is higher than iced tea because the particles are moving faster. Just like we talked about quite a few weeks ago. That's the reason why we mix sugar with hot tea and not cold tea. The particles are moving faster. Notice how we're coming back to this and bringing a lot of stuff back together. Now, the SI unit we use in science is kelvins. Another popular one is Celsius. You will not see Fahrenheit in here. And the reason why is because Fahrenheit was based off of a certain element. Does anybody know what that element was? Mercury. Early thermometers in the United States were made out of mercury, which is why if they broke, it was considered extremely dangerous and you could have mercury poisoning. Celsius is based off of water. At 0 degrees Celsius, water freezes. At 100 degrees Celsius, it boils. So for some reason, since us in the U.S. decided to be special, we based ours off of mercury, the thing that causes people to go crazy. Kelvin, on the other hand, what's up? Yeah, go for it. Grab a pass. Yeah, it's based on, essentially, the movement of everything. At 0 degrees Kelvin, everything stops moving. Like everything. That is the theoretical coldest anything could ever be. Well, first off, we'd all be dead long before it hit 0 degrees Kelvin because the subatomic particles, electrons, protons, and neutrons, stop moving. Oh, so now we're talking about the great, that's a theory that they're using, is that eventually the universe is going to expand to the point to where there's not enough energy, molecules aren't bouncing off of each other, and everything will essentially just freeze in place for all of eternity. I think that's called the Big Freeze. There's also the heat death of the universe, which has to do with entropy. Entropy is the amount of disorder, essentially, that something has. What's up? Most likely, but definitely not in our lifetimes. We're talking about in scales unimaginable to human minds. All right, so when air is a higher temperature, the air molecules transfer their energy to the colder when they impact it, just like we're seeing right here. In this instance, which is colder, the air or the ice cream? The ice cream, because the air around it is warmer. It's coming into contact with it, and it melts it on the surface. It doesn't melt it all the way through. And eventually, we are turning it into a liquid instead of a solid. And that's quite possibly one of the saddest melts of ice cream I've ever seen. Thermal energy is where we're going to start our discussion. Thermal energy is the sum of kinetic and potential energy of the particles in an object. So, KJ, in this instance, this right here is coffee. Is coffee normally served hot or cold?
Hot.
Hot, but then you can ice it to make it colder. So, the thermal energy of the coffee is going to be greater than that of the cup. Thermal energy increases when the average kinetic energy increases. So, thermal energy equals kinetic energy plus potential energy. If in this instance, a coffee cup on a high shelf has more thermal energy than a coffee cup on a low shelf. Just think of it like that. Potential energy is the potential to do work. It's a really bad example, but you just got to remember potential energy just means the potential to do work. So the more mass an object has, the more thermal energy it contains. Najee, when you walked in today, you said that it was warm in here. Was I correct in that assumption? Okay. The more mass that a body contains, you will have more kinetic energy, more thermal energy, which is why the larger goldfish in this example has more thermal energy than the small goldfish. Well, yeah, I mean, I guess that's one way to put it. With two C's, is that what we're talking about? Thick with two C's? Oh, three of them. Oh, Lord Jesus. All right, so heat. The measurement of heat is just thermal energy that flows from something with a high thermal temperature to something with a lower thermal temperature. So in this picture right here, what do we think heat is being transferred from? The fire. Where is it being transferred to? Not just the humans, the air, the area surrounding it. So everything surrounding this fire is absorbing that heat because it is cooler. Heat is going to flow from areas of high concentration to low concentration, and you're going to see that in just about everything. As something absorbs heat, its temperature is going to change depending on the substance. So for instance, what we looked at right here in this, what are they cooking? It's not hot dogs. Look real close. It's kind of hard to see. Marshmallow. Now, do we think that it takes the same amount of heat to increase the temperature of that marshmallow by 1 degree as the marshmallow as it does a human body? No. No. Why? What if we have the same mass? Well, let's think about it. If we have the same, like let's say we have 1 gram of marshmallow versus 1 gram of human flesh, which by the way smells like bacon cooking if you cook it. Don't ask me how I know that. Like I said, don't ask. So if we have 1 gram of marshmallow cooking and 1 gram of human flesh, well, let's keep them separated. We're holding them both over the fire. Which one is going to take more energy to increase in temperature? Why do you think that? So you think it has something to do, marshmallows are basically air. You think it has something to do with the how spread out those molecules are? Okay, you're on the right track. When we talk about the amount of heat that's required for something, we're going to talk about something called specific heat. Now, specific heat is unique to each individual compound. For instance, water, compared to 1 kilogram of sand, the amount of heat needed to raise 1 kilogram of water is 1 Celsius is 6 times greater, which means that sand gets hotter a lot faster than water. Water needs 6 times as much heat energy to increase its temperature than sand. Anybody in here ever been to the beach? Okay, when the wind flows over that water, does it feel cooler or hotter? Cooler. That's because the water is a coolant. That wind picks up the cool, well, the water pulls that heat off of the wind, to be more precise, and it is cooler. If your feet are too hot in the sand, where do you need to go?
In the water.
In the water, because the water is cooler. Sand only takes a certain amount of heat, same as water, and that's known as specific heat. In joules per kilogram degrees Celsius. That means for every kilogram that you have of something, it's going to take this much energy to increase it Celsius, in 1 degree Celsius, which is equal to 1 Kelvin. So for in this instance, aluminum, what's up? What? Okay.
Do you not know how bad that is?
Yeah, sure thing. We'll discuss NBA trades in just a bit, okay? So in this instance, aluminum has a specific heat capacity of 900 joules per kilogram Kelvin. This means that aluminum takes a lot more energy to increase it. This is why aluminum is used as an insulator whenever you have leftover foods, because it's not going to increase that temperature as much. I wouldn't know. I'm not of that particular go around, you know. Lord Jesus. But in this instance, aluminum, it takes a lot more energy to increase its temperature as opposed to steel in different forms. These are different mixtures of steel. So water has the highest specific heat of other common materials. This is what makes water such a good coolant. It tends to absorb a lot of energy in order for it to increase its temperature. So, what?
Add water to antifreeze in your radiator.
Yeah, well, not just that, but antifreeze, and if you take chemistry, we'll talk more about it. It becomes a solution, and when something's a solution, antifreeze is a really good example. It decreases the freezing point as well. And when it decreases its freezing point, that means that when it gets colder, it's not going to freeze up and lock up your engine, which is why it's dangerous whenever it gets, you know, colder to just put pure water in there. What's up, BJ? Oh, dear Jesus. What's up? Yes. Yeah, you can go take a leak out in Canada, and if it's cold enough, it'll freeze. And in places like Antarctica, I mean, it'll freeze straight off, if you catch what I'm saying. So, yeah. Yeah, steam is just the water vapor evaporating off. Yeah. Oh, Lord Jesus. All right. This is the formula for the changes in thermal energy. I'm going to show you an easier way to calculate this and specific heat in just a moment. But to start us off, where did I put everything? So we have our mass. If we want to calculate the change in thermal energy, so change in temperature, delta T, is equal to our mass times change in temperature. This is energy. Times the specific heat, which is measured in a lowercase c. Now, the easiest way, and this is not in your notes, for the people that are viewing at home at some point, I'm going to click this real quick. Hey, you go watch the videos I posted under materials. This is what we're going to do. And again, this is not in your notes. This right here is the triangle method to solve.
Can you find it online?
You can find it online. This is the triangle method for specific heat. Our energy, it's going to be on top, is equal to mass times, and I'll put C, I'll put the specific heat, this is specific heat, times the change in temperature, delta T. In this instance, remember, up and down lines are multiplication, side to side lines are division. In this case, if you're given all but one of the values, you can immediately set it up instead of having to balance equations and all that good stuff. This is an extremely useful shortcut. We use it in chemistry as well. This is also the main way that we're taught with equations and stuff, but I want to teach a shortcut because it's easier for me. And we're going to use that in just a minute. This is normally, and unfortunately, I can't do this this year. This is normally the part where we would create our own calorimeter and we would set stuff on fire. But unfortunately, thanks to COVID, we can't really do it. Now I'm going to show you a video of it because I don't have the material for it.
Can we start on this worksheet whenever we want?
Yeah, but I'm going to...
We're going to learn about calorimeters, what they are, how they might be used, and why they are used. A calorimeter is a device used for calorimetry, the process of measuring changing heat of chemical reactions or physical changes, as well as heat capacity for a material. When you look at food items, their energy content was worked out by burning the food.
We also do this in biology, so hopefully next year we're good
This
to go to do
corresponds to
this.
the energy content label and is given in calories. To do this, you have to use a calorimeter. The simplest calorimeter consists of a thermometer that...
So, what we're detailing right here is whenever you eat something, you're consuming calories. Calories are a measurement of how much energy is in there. This is how we figure out how much calories are in one thing. If you ever look at it and wonder, how do we figure out that there's 100 calories in this? This is how.
attached to a metal container full of water and is suspended above a combustion chamber. In a typical calorimetry experiment, you can measure the energy that is released from fuels. Can you think why this might be important? The answer is that different fuels release different amounts of energy. So if you're flying a plane, you need a fuel which releases more energy than, say, if you were driving a car. This is because the plane is heavier than the car, so more energy is needed to make it move. In the classroom, if you do this experiment, you would do it on a much smaller scale, using a spirit burner. This is what you would need to do. 1. You'd measure the mass of a spirit burner before the experiment. 2. Add a certain amount of cold water into a copper calorimeter, a small metal can, and suspend it at a fixed distance from the spirit burner. Can you think why it is important for it not to be too far away? Pause the video and continue when ready.
We're not going to pause it.
The answer is that in this sort of experiment, a lot of the heat is transferred to the surroundings. So you need to minimise this by either placing the spirit burner as close to the calorimeter as possible, or you could reduce this by insulating the sides and adding a lid. 3. You'd measure the starting temperature of the cold water. 4. You'd use the spirit burner to heat the water for a fixed amount of time. 5. Record the mass of the burner afterwards so that you could calculate the mass of the fuel combusted. And finally, 6. Record the temperature change of the water caused by heating. Can you think why you might do the experiment more than once? Pause the video and continue when ready. The correct answer is that you want your results to be as accurate as possible. This also improves the reliability of the results you collect. If you have a larger temperature change on doing this experiment with one type of fuel than another, this means that more heat energy was transferred to the water than if you have a smaller temperature change. The best fuel is likely to release more energy per gram of fuel. In summary, Calorimeters are devices that can measure the heat of chemical reactions, physical changes, or heat capacities for different materials. A simple experiment showed how measuring the temperature change of water could be used for this purpose.
All right, it's going to bring us to conduction. We'll also talk about conduction when we get to the electricity and magnetism unit. That's the transfer of thermal energy by collisions through particles. So in this instance, we are looking at conduction of energy as they impact one another. They are transferring that energy to the other balls that are bouncing. Since they're always in constant motion, they're always going to be reacting to each other. So they may slow down at some point, they may speed up, but the more energy we add, the more movement that happens in these particles. And some items can conduct heat better than others. In this instance, we're talking about metals. Since I think we may have been on quarantine or on virtual whenever we talked about the electron sea. Metals, which I'll tell you a fun fact in just a minute. Metals are really good conductors because electrons aren't bound to just one atom. As a matter of fact, in space on the ISS, something was discovered that I forget what it's called. I think it's called cold welding. So normally when you weld something, you increase the temperature and either melt it together or you add something to it to weld it together. However, in space, since there's nothing in between each of these, if you were to take two pieces of the exact same metal with no covering, there's nothing on the outside, there's no oxidation, and you hold them together, they'll actually weld together in space right then and there with no heat added because the electrons don't know which metal they're attached to. So they just attach together, which was really cool. It blew my mind when I figured this out. Convection, yeah. And it can only, well, I mean, I guess you could do it in other areas, but it would have to be in areas that the metal can't come into contact with anything else. It has to be completely pure. Right. Yep. Well, not even cold. Doesn't even have to be that. It just has to be in the presence of no other materials. Convection, you probably learned about that a little bit from your life science class, either, what was it, last year or the year before. Convection cells are what keep heats moving. It's the transfer of thermal energy from a warmer area to a cooler area. More energetic particles collide with less energetic ones. All right, energy can transfer without having to pass through matter, however, just like in the vacuum of space. I saw somebody on Twitter had made the question if it was, how does light pass through space if there's nothing in space? And that was kind of mind-blowing to me that somebody has gone their whole way through life without actually understanding what space is and what light is. But light is just a form of energy, same as heat, and it can be transferred without having to pass through matter, such as the vacuum of space. Yeah, that's how we receive heat from the sun. Yeah, well, due to our tilt and where we are in the orbit, yeah, we're receiving less direct heat. Radiation we talked about, transfer of energy, some of it's reflected, and that's going to bring us to the end of that section. So, yep.
You just said, okay, so Adam and Eve, they had kids. You said who their kids have kids with?
Wait, what?
Adam and Eve, right?
Uh-huh.
They had kids.
Uh-huh.
He asked who their kids have kids with.
Uh-huh.
I said he chose.
Yeah. I mean, you wouldn't be wrong.
Everybody is here.
We'll talk a little bit more about that theory and stuff in just a bit. Let me go ahead and get started on the specific heat worksheet. So, one of our virtual students. So you said that yours is blank?
Yeah, like I clicked on it earlier to see what we was doing because I had nothing to do. And then it just popped up some little letters, and then I couldn't get it back. Like I clicked undo about 50 times to get it pop up.
Yeah, let me see.
And then it's just like, I'm trying the black candy.
Cartier, what have you done?
You see?
What have you done?
I ain't do that
Cartier, how'd you do this?
there. Let me go.
What have you? I guess I'll go and copy and paste it from somebody
Well,
else's.
no, I've already answered it.
Oh,
I've already answered the
okay.
question.
All right then.
Like, yo, Maya's being copy paste.
No, because Maya's done.
I know.
Exactly.
I can just text.
Boy, hush.
I can just. Think it's okay.
This works due today, right?
Yeah. All right.
Simple.
Cartier, you are ready to go? All right. Let me show you. I'm going to walk through one with you. All right. I'm going to read the instructions. Directions. Use this formula to solve the following problems. However, I'm going to show you the shortcut in the triangle method. Again, people that are online will need to view the YouTube videos that I have posted. I'm going to stop the share